Hello, everyone. It is my pleasure to introduce Curtis. Curtis is a machine learning engineer here at Snorkel, and he works on the information extraction team with a focus on tackling customers' unstructured data needs. So without further ado, please join me in welcoming Curtis.
Awesome. Hello. Thank you, everyone, for joining me today. Yeah, so today we'll be talking about PonderNet. It's one of the more recent DeepMind papers. Always excited to see what that lab is capable of, because they always have some interesting insights into the state of the art and have some really unique ideas. I think PonderNet is no exception there. This is also a paper a bit on the shorter side, so I don't expect that we'll need the full time that we have allotted for this. But definitely encourage any sort of discussions or questions that we might come across throughout the way. So yeah, don't be afraid to speak up. Awesome. So getting right into it, PonderNet, or Learning to Ponder. This is a paper by Andrea Banino, Jen Balaguer, and Charles Blundell. It was originally published in ICML this year. So pretty new. So I think there were a few things that really stuck out to me when I read PonderNet that kind of made it an exciting paper. First of all, it's just that this is a really general technique that can be applied to a wide variety of methods, techniques, network architectures, etc. As you see, as we get into the actual formal definition of things, it's actually pretty simple and doesn't have that many hard requirements on what our architecture actually looks like. Secondly, it kind of intuitively makes some sense. I think in our field, especially, a lot of methods can kind of seem black boxy, and you can kind of struggle to wrap your head around why something might work. But being able to ponder over a problem and spend more time thinking about a problem is something that all of us do intuitively day to day. So it's kind of refreshing to see something like that appear in a neural network that's able to achieve really great results as well. Additionally, this technique has been shown to be able to save on computational costs. I think this is especially a hot topic today, given that especially within the NLP field, we're seeing more and more models reach billions and billions of parameters, or sometimes even up to like 1 trillion parameters. And the computational costs to train these and to even do inference on them can be really tremendous. And this has dramatic impacts on many things, from cost to environmental impact, etc. So being able to get state-of-the-art results on some tasks while also potentially doing it in fewer computational cycles is really exciting. Similarly, again, I think I mentioned this a little bit already, but we're able to get some state-of-the-art results using PonderNet. These state-of-the-art results are on tasks that you might not be the most familiar with, as they tend to be more focused on tasks that have adaptive computing time, or for their tasks that algorithms that implement adaptive computing time tend to do pretty well on. So we'll go over each of these a little bit more in depth and kind of highlight some of the tasks that this model performs on a little bit later in the presentation. So yeah, so just overall, our problem statement, most neural networks have computation cost that grows with the size of the network. Ideally, we should only spend additional compute to scale with the complexity of the problem being solved, rather than the size of our input. And this is something that, as we'll see, PonderNet is able to achieve. So like most works, there's a lot of related work that has been done specifically in this field of having variable compute time for a given problem. The one that is most heavily discussed in this paper and is probably the closest is this adaptive computation time, or ACT, by Alex Graves, which kind of defines a similar way of essentially ending your computation early, or having a modifiable compute time, but tackles the actual computation for when to halt a little bit differently. And as we'll see, PonderNet ends up outperforming this one in many of the tasks. In addition to this, a number of different authors have explored using reinforcement learning-based approaches like reinforce to decide which parts of a given computation we can skip. So you can think of, in this paper, learning to skim text, the authors build up a reinforcement learning-based approach to decide which layers they can effectively skip when they're actually doing their training and inference. So it's definitely a cool like subfield, and one that's has a lot of active research going on in it. So yeah, let's jump into some of the more formal sort of architecture setup. And essentially, it's pretty simple for PonderNet. All that we really require is this step function S. And this step function S will just take some hidden state N and your input X and produce some prediction, the next hidden state, as well as this this lambda sub N for each step. So we can think of this as your y sub N as your prediction at that given time step N. Your H sub N is your hidden state at the next step in your computation. And then I think most importantly and most unique to this, this approach and adaptive compute in general is this lambda sub N. So what this lambda sub N represents is the probability of halting at that given time step. So as we look below, we kind of have a smaller illustration here of what that might look like. So this box with the circles in it can represent our actual neural network. And I think the overall simplicity here is something that I really like about this paper. This step function S that we've represented visually below really can take the form of any sort of recurrent function. So for this, we can use something like LSTM or a gated recurrent unit that you might be familiar with, or even a transformer network, which is what they actually end up using in this paper. So in addition to having that sort of flexibility, it also means that this technique will benefit by any future advances that we make in sort of architecture advances. So I find that to be like really compelling overall. Yeah, so just looking again at this illustration, we'll output essentially our prediction for each time step and output a probability that we halt there. So lambda sub 1 through sub 4 here. So, you know, maybe at the beginning of the network, our probability of halting is just 0.1. So then we essentially flip a biased coin at that point to decide whether or not we actually halt. So in this first step, we'll be halting with a probability of 0.1. And then assuming that we don't in fact halt, we'll go ahead and pass those hidden states through, produce a new prediction at y2, as well as a new halting probability of lambda sub 2. And perhaps that goes up now, so maybe we're a little bit more likely to halt. And then once we flip that biased coin and it comes up positive and says that we halt, then we just pass the actual y of that step as our final answer. So in this way, we're able to kind of keep passing our inputs through and through these recurrent hidden states until we get to an actual response that the network deems is acceptable. So we can look at this a little bit more mathematically by examining this loss function. So the loss function is kind of broken up into two main parts, which is our sort of reconstruction error on the left and our regularization factor on the right. So here, when we're actually computing the loss, you'll see that this P sub n is the probability that we have halted at that given time step. And we multiply that by our individual loss at each of those individual time steps while we're training. You'll note that this training is a little bit different than the inference. I have the next slide where we'll go into that a little bit more in detail. But here, when we're actually computing this loss, we will compute the loss for each time step, even though at inference time, we will halt when the network essentially tells us to halt. Oops, sorry. So I guess to go over to the regularization side of things, things get a little interesting as well, as they introduce this P sub G lambda sub P, which just represents a geometric distribution. Now, this lambda sub P is a hyperparameter that you can pass to the network, that you pass to this to whatever your network is, and kind of determines what your baseline completion or like dropout rate should be for. Maybe dropout's not the best term to use here, but your baseline distribution for when you halt should look like. So here in the bottom right, I've just pulled a few different values for lambda sub P that you might see. And you'll see that your probability of halting is higher in the beginning and then sort of diminishes as your time steps go on. So it's kind of forces the network to eventually come to some sort of computation rather than just continually saying, hey, I'm not sure about the answer, and we're going to hold off on actually computing this answer until the end of time, essentially. So with that being said, we do need to enforce an actual maximum number of time steps. So when we look at this actual training function, what we'll actually do is unroll the network to some maximum n. Now, in the paper, they choose n of 20 to be like their maximum step number. Now, if during inference time, the network reaches that maximum number of steps but has not decided to halt yet, then we will just output the actual y sub 20 for that final step and sort of force it to terminate. Now, again, as we're training, we're unrolling and calculating our loss over this full 20 steps, regardless of what our actual lambda sub n's are. So even if we had, say, like lambda sub n of like 0.9999 for this lambda sub 4, this fourth step, and we were highly likely to actually halt there if we were doing inference, during training time, we'll continue the network's computation all the way through 220 and to calculate our full loss function. And again, that full loss is kind of represented over here on this left-hand side of this loss function, where we're multiplying the actual probability that we've halted on that given step times the actual loss for that given output.
So just to clarify, we're taking like a loss at every single time step, right?
Yeah.
Okay, gotcha.
Cool. So for the actual experimental setup, the authors rather ran PonderNet over a pretty large variety of training tasks. They're kind of grouped into these three different tasks that are parity, Babby question answering, and paired associative inference. So while it doesn't sound like a lot of tasks, the Babby question answering dataset I think is particularly interesting in that it covers 20 different types of natural language inference, which it's a lot of different things that we end up actually covering just by including these three data sets. Something to note is that each of these kind of experiments has their own papers that I encourage you all to check out. And those papers have shown that all of these data sets basically require adaptive compute in some manner. And more traditional neural networks don't really perform very well on these at all. So that's why perhaps you're not used to, we don't see like squad for question answering here. But I think that also brings up a point in this paper where while I understand the rationale behind choosing some of these data sets, I'd also be curious how it performed on some of those experiments that we're more used to seeing, just to get an idea for where the state of the art lies in comparison there. Yeah, so the first task that we train on is what's called the Parity Task. So essentially, this is pretty simple to explain in theory. We just generate a series of ones, negative ones, and zeros of some length. And then our output is just whether or not the count of ones, or the number of ones present, is odd. So in this example over here, we have 3 ones. So 3 is an odd number, so the network should learn to output 1. Now, one interesting caveat here is that we generate these for many different lengths of input sequence. So I believe in the paper, they generate these sorts of training examples for values of n up to, I believe, 60 or so, or rather 90, I think it is, and kind of split those into 2 different kind of evaluation metrics, as we'll see on the next slide. So the idea here is that the network should be able to learn this relationship independent of the length of the actual input sequence. So here we have some of the actual parity experiment results of PonderNet compared to ACT, which is that adaptive compute time network that we mentioned in the prior work. So this breaks the parity experiment into 2 different steps here, or 2 different experiments, essentially. On the left-hand side, A, we have the setup where we train the network on shorter strings. So these are strings of 1 to length 48 in the paper, and then actually test on strings of that same length. So train on strings of length 1 to 48, test on strings of length 1 to 48. And here we see that the results are pretty close, but PonderNet kind of ekes out ACT in terms of accuracy and actual compute. And we're also able to score quite high on this. But where things actually get interesting is on this second example of B. So here the experiment setup gets modified a little bit. Here we'll generate those strings for lengths 0 up to 99. And we will only train the network on strings of length 0 to 49. So we're only training on these shorter strings. And then when it comes to actual test evaluation, then we test on the longer length strings of 49 to 99. So, testing on strings that of length that appeared nowhere in our train set that the network has never seen before. And here we're actually able to see how much better PonderNet is able to perform. We're still able to get like a really high accuracy, whereas the ACT network is basically no better than random chance. And we're also looking at the number of compute steps here. And we can see that this is a more challenging task. And as a result, PonderNet requires a larger number of compute steps than it did for the easier task, which makes a lot of sense. And it kind of shows that the network is doing a lot of what we kind of hoped it would do. Similarly, on the right here, we see total number of compute steps. Here you're able to see that PonderNet's able to reach that actual acceptable performance accuracy much faster than ACTs, and basically always better than just a traditional RNN, which doesn't perform on this task at all. They also go ahead and show off that the PonderNet is pretty robust to your selection of lambda sub p. So if you'll remember that lambda sub p is, again, just this hyperparameter that goes into your regularization factor, which kind of dictates how early this network should terminate. And we're able to see that for the most part, we're able to get pretty good accuracy somewhat independently of what value we choose here, with the exception of 0.9, wherein we are essentially forcing the network to terminate after only a single step, and it's not able to actually compute all the steps that, or it's not able to compute all the steps required to actually come out with a reasonable response. Similarly, on this right-hand graph here, they show that for lambda sub p of 0.1, so in this case, you would expect on average for your network to go about 10 steps. It shows that the network is able to sort of override that, that regularization factor and not take all the steps necessary if it's able to minimize the loss otherwise. So in this case, we're still favoring fewer steps than our hyperparameter would suggest, which I think also further supports their claims that it's pretty robust to this actual hyperparameter selection. And I think the paper also mentions that this hyperparameter selection is also one of the kind of key differentiating factors between this and ACT. It seemed like ACT during training time was pretty sensitive to some of the hyperparameters that you would pick during training time, and your results would potentially suffer as a result. So the next task that they train this network on is called paired associative inference. So for this, the network is shown a series of pairs of images. Now, for this setup, rather than showing it the full pixel values, we actually use a separate network that is kept constant to generate image embeddings over image network, or over ImageNet, sorry, and use that data set to kind of construct these pairs. So they're shown these sequences of relations, essentially. So you can think of this as picture A related to picture B in some way, and et cetera, et cetera. And then the network is shown a series of 3 vectors, and one is kind of your target vector. And the network then has to choose which of the other 2 vectors is related. So here in this first example, we have a direct relationship where these showed up in the exact same episode. So this is sort of a trivial example. Same here, where this dog showed up in the same photo as this guy in this example. So those are like the sort of trivial examples, but then it also includes examples where you have to do sort of this multi-hop reasoning. And so in order to get this association from A1 to C1, you have to associate A1 to B1 and then B1 to C1 in this next set. So some nuance there, and I think the authors of this initial paper, which introduced this task, kind of really argued for this being some like core foundational reasoning type tasks, because it kind of tries to model the way that everyday humans kind of experience events and relations to their environment. So here we're able to see that PonderNet also performs really well. It doesn't quite beat out Memo, which was a network specifically designed for just this paired associative inference task. But PonderNet's able to actually significantly outperform this universal transformer here, UT, which is just like a transformer network. So it actually has the same architecture that PonderNet is using, just it doesn't have the sort of variable compute time that PonderNet brings to the table. Cool. So then next we have this Parity task, which, as I mentioned, is comprised of 20 total task types. I've selected 3 here that I think kind of showcases the diversity that's contained within this set. So we have sort of basic factoid, where they have with a single supporting fact, where we just have some sentence that sets up a scenario and asks something super basic about it. We have factoid QA with 2 supporting facts, where we have to sort of reason through, we have to sort of reason through the text that's been provided and maybe make some multi-hop sort of inference there. And then we also have some considerably challenging tasks like positional reasoning, where the text just describes the relation of several objects to one another, and the network has to answer these sorts of yes or no questions about where these objects are in relation to one another. So overall, this is like a pretty robust set of things that, that this data set actually tests. And here we're able to see that the PonderNet is actually able to solve every single task and has the lowest average error. And this is where we see perhaps the most compelling state of the art here. So yeah, that's more or less all that I have prepared for today. I think that this is a super interesting network architecture. I think it has, pretty wide-ranging impacts across this specific subdomain, and I'd be really curious to see, how we can leverage this sort of adaptive compute time to impact other like more mainstream tasks. So I think that would be like my biggest ask for like for further explorations into this field. Yeah, so thank you all for joining. I had a lot of fun diving into the paper here and the details and really getting to know this subfield. But would love to further discuss any of the topics that we've touched on here today if anyone is curious or just wants to chat.